All right, now it's time to put together some of the pieces we know. So, how can we find these values? I want exact values. I do not want calculator values. So we want exact. Exact values. Which is to say, if it's got a square root of 2 in it, it needs to have a square root of 2 in it. If it's got a radical 3 in there somewhere, it's got to have a radical 3 in there somewhere. Decimal values are not good enough. If you write out a decimal value, if all you do is put this thing in a calculator and mash a button, you are not getting credit out of me. You are not getting credit out of me if all you do is mash a button on a calculator and write down a string of decimals. What I want you to do, what I want you to be able to do is to synthesize this information that we have. For among other things, there are going to be times in the future where you're not going to have access to a calculator. I know this because I've had students in the past that have come back to me. They went off to university somewhere and they took an exam in their engineering class, and the professor said, "You may not use a calculator." And this student of mine, she was so grateful. She came back to me a couple weeks later and she stopped by campus. I think she's going to University of Houston. And she came back and she said, I am so glad that you forced us to do that. Because when they told us we couldn't have a calculator, so many of the other people in class, their face just dropped. They had nothing. But she said I was able to draw that picture and pull together the information that I knew. And it turns out that is precisely what the professor was after. Now, that's not on me, that's on her. She learned it and she knows this information to this day, as far as I can tell. She knows this information. You will not forget this if you reason from what you know to what you don't know. If you rely on a calculator, and if there comes an exam when you don't get to use one, you're on your own. She was on her own and she was able to get by. So, all that said, you need to be able to find this information without reference to a calculator. If you start, now, there's no way through the video screen I can inhibit you from doing that. If you do that, I can't stop you. But you're just robbing from yourself. So make sure you need to discipline yourself and do these problems without reference to a calculator. Once you get them worked, if you want to use your calculator to check your answer, make sure it's right, God bless you. But you should be able to work these without reference to any kind of technology at all, except what you have in your gray matter. All right, so let's see if we can make this happen here. We know sine of 30 degrees is 1/2. We know sine of 45 degrees is 1 over radical 2. We know sine of 60 degrees is radical 3 over 2. I'm just using sine as an example. You could do this with any one of the other 5 functions. How do we know this? Why do we know this? We know this because we know the triangles. 30, 60, 90. This is 2. This is 1. This is square root of 3. Special triangle. 45, 45, 90. This is radical 2. This is 1. This is 1. You know those triangles. You can get any one of those 6 function values for any 3 of those. All right? We also know ASTC. We know that sine is positive in quadrant 2. So if I have a quadrant 2 angle, and I compute sine of a quadrant 2 angle, no matter what else happens, I know for sure my answer's got to be a positive number. If my angle is a quadrant 3 angle, I know my answer needs to be negative because sine is positive here and here, sine is negative here and here. So as we look through these angles, all I'm doing here is sine. You can choose whatever function you like. If you were working with tangent of 1 and 3 would be positive, tangent of 2 and 4 would be negative. So once you identify which quadrant you're in, and you need to do that every time, do quadrant check. Every time, quadrant check. Every time, quadrant check. 135 degrees, 210 degrees, and on down the list. This is a negative angle. This is a multiple revolution angle. Always do a quadrant check. That tells you the positive, negative. Remember the word is signum. Signum is the official way to say positive, negative, so that we don't need to confuse the word sine with the word sine. So when I say signum, I'm using the Latin form of this word. So when I say signum, the signum is either positive or negative. All right, so here we go. The key element is this. This is the big deal. This is the next big notion here. The function values of theta and theta reference are equal except possibly the signum. Except for the signum, the values are the same. The technical way to say it is they have the same absolute value. So if I have theta and theta reference, the function sine of theta and sine of theta reference are the same number, except possibly one might be positive, one might be negative. Now, theta reference, remember theta reference? Theta reference is always quadrant 1. Theta reference is always positive. So no matter what function you take of theta reference, that's a positive value. But the sine or tangent or secant of or whatever function of theta might be positive or negative. That's determined by this. So what we can do is this. If I want to find the sine of 135 degrees, well, a little sketch helps. Where is 135 degrees? It is somewhere here in quadrant 2. There's 90, there's 180, so 135 is between there somewhere. That's theta. I am in quadrant 2. Sine is positive in quadrant 2. So no matter what else, I know that number is, I'm going to emphasize, that number is positive. I know sine of 135 is positive because 135 is a quadrant 2 angle and sine is positive in quadrant 2. Once I've taken care of the signum, once you have taken care of the signum, you may ignore the quadrant issues. So we've done our quadrant check. The signum is positive. Now we may ignore the positive, negative. We're just going to find the function value. And so what we need now, the actual value itself is found from this statement. What is theta reference? What is 135 reference? If this is 135, then how much do you need to add to that to make the rest of the 180? You need to add 45 degrees. Theta reference is 45 degrees. And that means sine of 135 and sine of 45 degrees are the same number, but possibly different signum. We've already taken care of the signum, so that's off the plate. So without reference to the signum, without reference to the positive or negative, we know that the sine of 135 degrees and the sine of 45 degrees are the same number, and that's 1 over radical 2. And this doesn't take nearly so long if you don't explain it while you're doing it. You need to recognize what's the reference angle, what's the quadrant you're in. What's the reference angle, what's the quadrant you're in. All right? Let's do sine of 210. Where is 210? So, see what I'm doing here? Quadrant check. I'm doing quadrant check. Every time you do these, you do quadrant check. So quadrant check, where is 210? 210 is in quadrant 3. I'm doing sine in quadrant 3. I know my answer is negative something. What is the something? The something comes from, now get the reference angle. If this is 210, then how much did you add to 180 to make 210? We have theta reference is 30 degrees. Sine of 210 is the same thing as sine of 30 degrees, except for the signum. Sine of 30 degrees, we know, that's 1/2. So sine of 210 is also 1/2, except for the signum, which we've already taken into account. Okay? Same song, next stanza. 300 degrees. 300 degrees is a quadrant 4 angle. It's between 290 and 360. If this is 300, how much do you add to that to get 360? Well, theta reference is 60 degrees. What quadrant is that? That's quadrant 4. What is sine in quadrant 4? Sine in quadrant 4 is negative. So you see how this works together? Negative, whatever it is. And now I need sine of 60 degrees. Sine of 60 degrees is square root of 3 over 2. If you have any question, go to sine of 60 degrees. Sine of 60 degrees is opposite over hypotenuse. So that's negative square root of 3 over 2. Determine the positive negative based upon the quadrant. Determine the numeric value based upon the reference angle. And as long as the reference angle is one of these special ones, those are the ones I'm going to be asking of you. As long as these reference angles are the special ones, then this can be found using these pictures. Sine of negative 240. Maybe we need a little more space here. Let's play this a little more gently. I'm going to erase my solutions here. 240 degrees, negative 180, negative 270, negative 240 is in here somewhere. Negative 240, this is quadrant 2. This is a quadrant 2 angle. What is sine in quadrant 2? I know my answer is positive something. I'm just going to emphasize the positive. What is the reference angle? Well, if this is negative 240, we need that angle. How much do you, if I have negative 180 and some more, what is that? Is it clear that's going to be 60? Because if this is negative 240, I know this is 120 degrees, because that's a grand total of 360. If this is 120, that's 60. If this is 240, then this is 60. I've taken into account the positive and negative. Once you do the quadrant check, you've taken into account the positive and negative. This is 240, so that's got to be 60. So the reference angle is 60, and I know sine of 60 degrees is radical 3 over 2. Sine of 510 degrees. If you subtract 360, 510 minus 360, that is 150 degrees. That's another quadrant 2 angle. Sine is positive in quadrant 2. And what is the reference angle of 150 degrees? Draw a little picture. Every time you do this, you draw a little picture, it just falls right in your lap. If this is 150, then we know that's got to be 30. The reference angle is 30, 1/2, and it's all over but the shouting. And so, this can be true for any one of these functions, sine, cosine, tangent, secant, whatever function you want. If you know the 3 basic values for any function, then you can have these reference angle, the angles, coterminal angles that have the same reference angle, can be found. Now, now let's play this. There's another way to look at this that helps to delineate this in your mind. And this is not me. I picked this up from another instructor a couple of semesters ago, and I think this really does help. They're what are called reference angle families. Reference angle families. Now, what does that mean? Suppose theta reference is 30 degrees. There are 4 angles within one revolution that we're talking about. In quadrant 1, theta is 30 degrees. In quadrant 2, if this is 30, this is 150. In quadrant 3, if this is 30, then this is 210. In quadrant 4, if this is 30, this is 330 degrees. And so 30, 150, 210, 330. That's called a reference angle family because they all share 30-degree reference angles. That's a convenient way to think of it. And so the thing is, you tend to do these numbers so frequently they start to become familiar to you. And so the reference angle family for 30 degrees is 30 degrees because in quadrant 1, theta and theta reference are the same. Here's theta reference is 30, so theta is 150. Here's theta reference is 30, so theta is 210. Here the reference angle is 30, theta itself is 330 degrees. So is it then clear we could do the same thing with both 45 degrees? We could do the same thing with 45 degrees, and we could do the same thing with 60 degrees. If the reference angle is in quadrant 1, 2, 3, 4, quadrant 1, 2, 3, 4, I'll just do them in the same sequence. So in quadrant 1, if this is 60 degrees, then theta is itself 60 degrees, because in quadrant 1, theta reference is equal to theta. In quadrant 2, if this is 60, this is 120. In quadrant 3, if this is 60, this is 240 degrees. I should put degree symbols on. And in quadrant 4, this picture's not drawn particularly well. I can get a little better than that. That's 60 degrees. And in quadrant 4, this is 300 degrees. So that's a reference angle family. 60, 120, 240, 300. Again, you'll do this so often, these will become familiar to you. And then 45 degrees is the last one. So 45, if this is 45 degrees, here this is 45 degrees, so this is 135 degrees. Here, this is 225 degrees. And in quadrant 4, this is 315 degrees. Those are reference angle families. It's not very hard to see. 135 plus 45 gives you 180. 315 plus 45 gives you 360. 180 plus 45 gives you 225, and so on for all these. So knowledge and understanding of those reference angle families is particularly convenient when you're working with these kinds of ideas, when you're working with these angles, and later on when we start to solve equations, it becomes pretty much indispensable.